Download this code from codegive.com, link in the description below. Detecting memory leaks with Valgrind, a comprehensive tutorial. Valgrind is a powerful and versatile suite of tools for debugging and profiling Linux programs. Its flagship tool, memcheck, is specifically designed for detecting memory leaks, invalid memory accesses, and other memory-related errors. This tutorial will guide you through understanding memory leaks, using Valgrind, specifically memcheck, to detect them, interpreting the output, and fixing the underlying problems in your code. 1. Understanding memory leaks. A memory leak occurs when a program allocates memory on the heap, using functions like malloc, calloc, realloc, or new in C++, but fails to release it when it's no longer needed. Over time, these unreleased blocks of memory accumulate, consuming available system resources. If a program continues to leak memory, it can eventually lead to performance degradation. As available memory decreases, the system may start swapping memory to disk, significantly slowing down the application. Application crashes. Eventually, the program may run out of memory entirely and crash, or worse, trigger unpredictable behavior. System instability. In extreme cases, excessive memory leaks can even impact the stability of the entire system. Common causes of memory leaks. Forgetting to free or delete. The most common cause. If you allocate memory, you must eventually free it. Losing the pointer to allocated memory. If you overwrite the pointer to a block of allocated memory without freeing it first, you have no way to release that memory. Exceptions in C++. If an exception is thrown between allocation and deallocation, the delete operation might be skipped, resulting in a leak. Smart pointers are designed to handle this scenario. Incorrect resource management in loops. If memory is allocated within a loop but not freed on each iteration, the leak can quickly escalate. Global or static variables. Memory allocated to global or static variables might not be freed properly at program termination, leading to still reachable leaks, which Valgrind reports differently. Not freeing memory in error handling path. You allocated memory, but in case of error, you return without deallocating that memory. 2. Installing Valgrind. Before you can use Valgrind, you need to install it. On most Linux distributions, you can use your package manager. Debian/Ubuntu *sudo apt-get install Valgrind. Fedora/CentOS/RHEL *sudo dnf install Valgrind. Mac OS, using Homebrew Brew install Valgrind. 3. A simple C example with a memory leak. Let's start with a basic C program that intentionally introduces a memory leak. Compile this program. *wall enables all commonly used compiler warnings, which can help catch potential errors early on. *G adds debugging information to the executable, which Valgrind needs to provide more detailed reports. 4. Running Valgrind, memcheck. To run the program with Valgrind and check for memory leaks, use the following command. *Valgrind, invokes the Valgrind tool. *leak check equals full, specifies that memcheck should perform a thorough search for memory leaks at program termination. Other options include summary, the default, provides a summary, and yes, equivalent to full. *leak_example, the executable file you want to analyze. 5. Interpreting Valgrind output. After running Valgrind, you'll see a report in your terminal. The output related to the memory leak will look similar to this, the exact details might vary slightly depending on your system and Valgrind version. Let's break down the key parts of the output. Asterisk equals equals PID equals equals memcheck, a memory error detector, indicates that memcheck is running. PID is the process ID of the running program. Asterisk heap summary, provides a summary of heap memory usage. Asterisk in use at exit, 40 bytes in one blocks, indicates that 40 bytes of memory, 10 integers asterisk 4 bytes slash integer equals 40 bytes, in one block are still allocated when the program exits. This is the leak. Asterisk total heap allocations, 1 allocs, 0 frees, 40 bytes allocated, shows that we allocated memory once and never freed it. Asterisk 40 bytes in one blocks are definitely lost in loss record 1 of 1, this is the core of the leak report. Definitely lost means that there are no pointers to this memory block, making it impossible to free. Asterisk at 0x483b71f, malloc, in /usr/lib/valgrind/veg preload memcheck amd64 linux.so, shows the function that allocated the memory, in this case, malloc. Asterisk by 0x109151, main, leak_example.c5, this is the crucial information. It tells you the exact line of code in your program, leak_example.c5, where the memory was allocated and never freed. This points directly to the source of the leak. Asterisk leak summary, provides a summary of the types of leaks found. We'll discuss the different categories later. Asterisk error summary, indicates the total number of errors detected. 6. Fixing the memory leak. Now that we know where the leak is, we can fix it. In our example, the fix is simple: add a call to free, to release the allocated memory before the program exits. Recompile the program and run Valgrind again. This time, the output should show that no memory is leaked. The all heap blocks were freed, no leaks are possible message indicates that the memory leak has been successfully fixed. 7. C++ example and using new and delete. The principles for detecting and fixing memory leaks in C++ are the same. However, in C++, you typically use new and delete for memory allocation and deallocation, respectively. Let's look at a C++ example. Compile, using a C++ compiler like G++. Run Valgrind. Valgrind will report a similar definitely lost leak, pointing to the line where new int10 was called. To fix the leak, add delete arr, before the program exits. Remember to use delete for arrays allocated with new and delete for single objects allocated with new. 8. Understanding different types of leaks, in the leak summary. Valgrind categorizes memory leaks into 4 main types. Asterisk definitely lost asterisk this is the most serious type of leak. It means that there are no pointers anywhere in your program that point to the allocated memory block. The memory is completely unreachable and cannot be freed. This is almost always a bug that needs to be fixed. Asterisk possibly lost asterisk this indicates that there might be pointers to the memory block, but Valgrind can't be certain. This can happen if the pointer is stored in a way that Valgrind can't track, example within a complex data structure. Investigate these carefully, they might be real leaks. Asterisk still reachable asterisk this means that the memory block is still reachable from a global or static variable, or through a chain of pointers from such variables. The memory wasn't explicitly freed, but it's technically still accessible. Asterisk these are often not critical errors, especially if they are related to resources managed by libraries that clean up during process shutdown. However, you should still review them to ensure that the memory is not being held unnecessarily. Valgrind has the "show reachable equals yes" option to report these with call stacks, which can help in finding the reason. Suppressed. These are errors that Valgrind knows about but is ignoring based on a suppression file. Suppression files are used to silence known issues in third-party libraries or system code that you don't have control over. 9. Using Valgrind options for more detailed analysis. Valgrind provides numerous options to fine-tune its behavior and get more detailed information. Here are some particularly useful ones. *track origins equals yes*. This option is extremely helpful for debugging. It tells Valgrind to track the origins of uninitialized values. When you see an error involving an uninitialized value, Valgrind will show you where that value was first created. This is invaluable for tracking down subtle bugs. However, it adds significant overhead, so use it when you need it. *show leak kinds equals all*. This option shows a breakdown of all the leak categories: definitely lost, possibly lost, still reachable, suppressed, in the leak summary, which is helpful for prioritizing your debugging efforts. *gen suppressions equals all*. If you encounter errors that you know are not related to your code, example in a third-party library, you can use this option to generate a suppression file. The suppression file tells Valgrind to ignore these errors in future runs. Use suppress ions judiciously, only suppress errors you truly understand and are confident are not caused by your code. After running with this option, Valgrind will print suppression rules in the output. Save these rules to a file, example suppress ions.txt, and then use the "suppressions equals suppress ions.txt" option when running Valgrind. *log file equals valgrind.log*. Redirects Valgrind's output to a file instead of the terminal. This is useful for analyzing large or complex programs. *verbose or v** increases the amount of information printed by Valgrind. Useful for debugging Valgrind itself or getting more context. 10. Advanced example: memory leak in a linked list. Let's consider a more complex example involving a linked list. This is a very common scenario where memory leaks can occur. Compile and run this program with Valgrind. If you uncomment freelist leaky head instead of freelist head, Valgrind will report a significant memory leak. It will show definitely lost blocks corresponding to each node in the list. The call stack will point to the create node function and the insert node function, indicating where the memory was allocated but not freed. The freelist function correctly iterates through the list, freeing each node individually. This is the standard way to deallocate a linked list. Key takeaways for linked lists and memory management: *. Iterative deallocation. When deleting a linked list, or any dynamically allocated data structure, you typically need to iterate through the structure, freeing each element one by one. Temporary variables. Use a temporary variable, like next in the freelist function, to hold the next node in the list before freeing the current node. This is crucial because after freeing current, you lose access to current-next. Nullify pointers. After freeing the list, it's a good practice to set the head pointer to null to prevent accidental use of the dangling pointer. This can help catch errors early on. 11. Detecting memory overwrites and invalid memory accesses. memcheck isn't just for finding memory leaks, it can also detect memory overwrites and other invalid memory accesses. Consider this example. When you run this with Valgrind, Valgrind will likely report an invalid write of size error. This indicates that strcpy wrote past the end of the allocated buffer, overwriting memory that doesn't belong to it. This can lead to crashes, unpredictable behavior, or security vulnerabilities. Key things to observe in the report. Asterisk address of the invalid memory access. Asterisk size of the invalid memory access. Asterisk function call that caused the memory access violation. Asterisk stack trace of the code. To fix it asterisk. Use a safer function like strncpy or tinprint that allows you to specify the maximum number of bytes to copy, preventing the overflow. 12. Memory management best practices. Here are some general tips for preventing memory leaks and other memory-related errors. Asterisk always free what you malloc, or delete what you knew. This is the fundamental rule. For every allocation, there must be a corresponding deal location. Asterisk free memory in the correct scope. Asterisk ensure that the free, or delete, operation happens within the same scope where the memory was allocated. If you allocate memory in one function and pass the pointer to another function, make sure the second function is responsible for freeing the memory, and that it always does so. Asterisk initialize pointers. Asterisk always initialize pointers to null when you declare them. This can help prevent dangling pointer errors if you accidentally try to use a pointer that hasn't been assigned a valid address. Asterisk use smart pointers in C++. Asterisk smart pointers, like std unique _ptr, std shared _ptr, and std weak _ptr, automatically manage memory deal location, reducing the risk of memory leaks, particularly in the presence of exceptions. Asterisk avoid realloc when possible, or handle errors carefully. Realloc can be tricky to use correctly. If it fails, it returns null, but the original memory block might still be valid. You need to handle the null return value carefully to avoid losing the pointer to the original memory. If realloc has to move the memory to a new address, the old address needs to be freed. Asterisk use Valgrind regularly. Asterisk make Valgrind a part of your development process. Run it frequently to catch memory errors early, before they become difficult to debug. Asterisk code reviews. Asterisk have someone else review your code for potential memory management issues. A fresh pair of eyes can often spot problems that you might miss. Asterisk avoid global variables. Asterisk it's best to use scope as tightly as possible. If memory is dynamically allocated for a global variable, it might not be freed properly at the exit. 13. Dealing with third-party libraries. Sometimes, you'll encounter memory leaks in third-party libraries that you're using. You can't directly fix the code in those libraries, but you can try the following. Asterisk update the library. Asterisk check if there's a newer version of the library that fixes the memory leak. Asterisk use suppression files. Asterisk create a Valgrind suppression file to ignore the leak in the library code. This is a workaround, not a solution, but it can help you focus on the leaks in your own code. Asterisk report the issue. Asterisk if the leak is significant, report it to the library developers so they can fix it. Asterisk consider alternatives. Asterisk if the library is causing too many problems, consider using a different library that provides similar functionality. 14. Conclusion. Valgrind is an essential tool for detecting and preventing memory leaks and other memory-related errors. By understanding how Valgrind works, how to interpret its output, and by following good memory management practices, you can write more robust and reliable software. Remember to use Valgrind regularly, especially during development and testing, to catch memory errors early before they cause problems.